Imagine you are standing on an oil platform in the middle of the North Sea on New Year's Day, 1995, when out of a relatively calm ocean, an 84-foot wall of water materializes and slams into the structure with almost no warning. That event, recorded by instruments on the Draupner platform off the coast of Norway, did not just make headlines, it changed science. For centuries, sailors had come back from sea telling stories of monstrous waves that appeared from nowhere, dwarfed their ships, and disappeared just as fast. Scientists sitting comfortably on dry land dismissed these accounts as exaggeration, the product of exhausted minds and stormy imaginations. The math of the day said such waves were statistically impossible. According to conventional wave theory, a wave as large as what sailors described should occur maybe once every 10,000 years in any given patch of ocean. The Draupner wave was real, measured, undeniable, and it shattered that assumption entirely. Suddenly, oceanographers had to confront an uncomfortable truth. The ocean did not behave the way their equations said it should. Something far stranger was happening out there, and it had likely been sinking ships for as long as humans had sailed the seas. This was not just a curiosity, it was a crisis in understanding, and scientists had to go back almost to zero to figure out how a wave twice the height of everything around it could simply appear from flat water. What they found was one of the most fascinating chapters in the history of physics and oceanography, a story that touches on mathematics, chaos, and the hidden life of the sea itself. Before we go deeper, it helps to understand what exactly qualifies as a rogue wave, because not every large wave earns the title. Scientists define a rogue wave as any wave whose height is more than twice the significant wave height of the surrounding sea. In plain terms, if the waves around it are averaging about 20 feet, a rogue wave in that same stretch of water would need to top 40 feet to qualify. Some recorded examples have reached 80, 90, even 100 feet. To put that in perspective, you are looking at a wall of water taller than a 9 or 10-story building, moving towards you at highway speeds. Normal ocean waves are generated by wind. Wind blows across the surface, transfers energy to the water, and waves form and spread outward. The longer the wind blows and the more open water it crosses, the bigger those waves get. But rogue waves are different. They are not simply big wind waves. They arise through a collection of mechanisms that scientists are still working to fully untangle. One of the leading explanations is called constructive interference. Ocean waves travel in groups and at different speeds. Sometimes multiple wave trains from different storms in different directions will converge on the same point at the same time. When their peaks line up perfectly, they do not just add together. They amplify each other dramatically. The result can be a single towering spike of water that contains the combined energy of waves that were each individually harmless. Think of it like sound waves. Two speakers playing the same note can create a point in a room where the volume is almost unbearably loud. The ocean does the same thing with water. That alignment does not last long, which is why the wave appears and then vanishes, often within seconds. The history of seafaring is filled with encounters that, in hindsight, were almost certainly rogue waves, even before we had a name or explanation for them. One of the most striking documented cases involved the ocean liner Queen Elizabeth II during a North Atlantic storm in 1995. The ship's captain described seeing a wave approaching in the darkness that he initially mistook for the White Cliffs of Dover, a sheer white wall of water rising out of the night. The wave, estimated at around 95 feet, struck the vessel, but the ship survived, largely because the captain had the presence of mind to turn the bow directly into it. Most ships are not so fortunate. Researchers analysing maritime accident records found something striking. A disproportionate number of large ships, supertankers and container vessels, built to withstand enormous forces, had disappeared in calm or moderate weather with almost no distress call. The SS Edmund Fitzgerald, which sank in Lake Superior in 1975, killing all 29 crew members, is thought by some researchers to have been struck by a series of rogue waves, though the exact cause remains debated. What is not debated is the number. A European research initiative called MaxWave, conducted in the early 2000s, analysed 3 weeks of radar satellite data from across the world's oceans. They identified more than 10 individual waves exceeding 82 feet in height during that single 3-week window. Where conventional probability said such waves should barely exist, the data showed they were happening regularly, spread across every major ocean on the planet. The ocean had been hiding something enormous in plain sight, and we had only just begun to see it clearly. So we know rogue waves are real, and we know constructive interference plays a role, but the physics goes even deeper and gets genuinely strange. One mechanism scientists study is called nonlinear wave interaction. In the standard simplified model of ocean physics, waves are assumed to behave linearly, meaning they pass through each other and continue on their way without fundamentally changing each other. But real ocean waves are nonlinear. When two large waves interact, they do not simply add up. The interaction itself generates new energy that gets funneled into the tallest wave. A Nobel Prize-winning physicist named Vladimir Zakharov developed equations in the 1960s that described this nonlinear behavior, and those equations predicted something alarming. Under the right conditions, energy could spontaneously concentrate itself into a single extreme peak, a mathematical phenomenon sometimes called a breather solution. Breather waves were considered theoretical curiosities for decades, but they have since been observed in controlled wave tank experiments, and the patterns match what happens in the open ocean with striking accuracy. There is also the role of ocean currents. When waves travel against a powerful current, like the Agulhas current off the southern tip of Africa, one of the world's strongest, their energy gets compressed. The wavelength shortens and the height increases dramatically. The Agulhas is a notorious rogue wave hotspot, and it is no coincidence that some of the most well-documented ship damage from mysterious waves has occurred in exactly that stretch of water. The physics is elegant in a terrifying way. The ocean is not acting randomly or maliciously. It is simply following mathematical rules, and those rules occasionally produce something that no ship built before the late 20th century was ever designed to survive. Even with all of this knowledge, rogue waves remain one of oceanography's most active research frontiers, and that is what makes them so endlessly fascinating. We can now detect them using satellite radar, and researchers are building predictive models that might one day give ships a few minutes of warning before a rogue wave arrives. A few minutes does not sound like much, but at sea it can be the difference between turning your boat into the wave and being caught broadside. Ship design is also changing in response. Modern vessels are increasingly being tested against rogue wave scenarios, and offshore platforms like the one that recorded the didyouknow wave are built with higher safety margins than they would have been before 1995. There are also unexpected connections emerging between rogue wave physics and completely different fields. The same mathematical framework that describes how energy concentrates in ocean waves also appears in fiber optic light pulses, in certain types of plasma physics, and even in financial markets, where extreme price spikes follow eerily similar patterns to rogue wave formation. Mathematics does not care whether it is describing water or money. It finds the same shapes everywhere. What began as a dismissed sailor's tale turned out to be a window into some of the deepest principles of how energy behaves in complex systems. The ocean is not just a body of water, it is a living, nonlinear, chaotic engine that still holds genuine surprises for us. And honestly, that is one of the most thrilling things about science. The moment something impossible gets measured is the moment everything gets more interesting. If you found this as mind-bending as we did, hit the like button and subscribe so you never miss a fact that rewrites what you thought you knew.